Hi, we are going to start off with quadratic equations, the parent graph y equals x squared, and then see what transformations we can perform on it and what it looks like in the equation. So this is a picture of the basic parent graph of a quadratic equation. Y equals x squared has a turning point at 0, 0, and then it goes up in this pattern. Oops. So question number 1 is we're going to add and subtract numbers to it and see how the graph changes. So problem number 1, you have the graph on the left, which is y equals x plus 3, all of that squared. And if you notice, the blue dotted graph is the original parent graph, and the red graph is the new equation. And we can see what changes were made. So on the graph on the left, the x plus 3, all that squared, if you notice, the whole graph shifted over 3 units to the left. And on the second graph, y equals x minus 3, all of that squared, the graph shifted over 3 units to the right. So if you have a number being added to the x with it inside the parentheses, that is always going to move in a left or right motion. If it's a plus number, it's going to move to the left, and if it's a subtract number, it's going to move to the right. All right, so we'll write it like this. So if a number is added or subtracted from x, the graph shifts to the left if a number is added, and shifts to the right if a number is subtracted. Okay, pause if you need to, or moving on. With problem number 2, notice the equation y equals x squared plus 3 is the first graph. And then y equals x squared minus 3 is the second graph. And again, the blue dotted graph is the original parent graph. If you notice, the parent graph got shifted up 3 when a number was added. And it went down 3 when the number got subtracted. And also be aware that the number 3 and the number minus 3 are not inside with the x. They're outside the square term. So there's a significant difference where the 3 is located. So on this problem, if a number is subtracted from the square term, if a number is subtracted from the square term, the graph shifts down that many units. If a number is added, to the square term, the graph shifts up. That many units. Okay, pause if you need to, or moving on. Problem number 3, the equation is y equals negative x squared. And if you notice, there is a negative on the squared term. And if there's a negative on the square term, the graph gets reflected over the x-axis. X-axis. So a negative on the squared term reflects the graph in the x-axis. Okay, pause if you need to. Or then moving on to the final transformation. Number 4, this one's always the harder one to see. The first graph on the left, you have y equals 2x squared, so there's a 2 factor in front of the squared term. And on the second graph, you have y equals 1/2 x squared, so there is a half factor in front of the x squared. And notice how it compares to the parent graph. The y equals 2x squared graph is thinner, more narrow than the original, and the y equals 1/2 x squared is fatter. And that's because you're speeding it up in the first graph or you're slowing it down in the second graph. So if you're speeding it up, it's going to rise more quickly, and therefore it's going to be skinnier. In the second graph, you slowed it down, so it's going to become wider because the rate is going slower. All right, so whoops. If a number bigger than 1 is multiplied, it will become more narrow. I'll say greater than 1. All right. It becomes more narrow. And if a number between 0 and 1 is multiplied to the x term, it becomes more, or becomes wider. Okay, those are the 4 transformations you need to know. Shifting left and right, shifting up and down, reflecting over the x-axis, and the graph getting either more narrow or wider. So now we're going to put this all together, and then based on the equation, you have to tell me what transformations occurred. Okay, in problem A, we'll highlight the change. The change is that there is a +2 number being added to the x. So if you recall, this is the first transformation we talked about. If there is a number being added inside with the squared term, this means that the graph gets shifted to the left two units. Okay, on problem B. Okay, this has a -5 at the end, not inside the parenthesis set. That's the big difference. If it's on the outside, then this means the graph got shifted down 5 units. Okay, on C, we have 2 changes. We have the -4 inside, and then we have the +7 on the outside. So this means that the graph got shifted. If it's a -4, it's to the right. 4 units. And outside the parentheses, the +7, that means it got shifted up 7 units. So that means the graph started at 0, 0, but then moved to the right 4 units and up 7 units. On D, there are two changes. There's the +6 on the inside, and then there's that negative on the outside. So this negative means that it was reflected in the x-axis. That's the symbol for reflected in the x-axis. And then the last one, the +6 on the inside, that means it got shifted to the left 6 units. All right, on letter E, again, anything that's not just an x squared is a change. So on this problem, we have the -1 at the end, and then we also have a factor of 2. Okay, so this factor of 2, when it's multiplied, it means that you're making it go twice as fast, so it's going to get skinnier. So this means that the graph becomes more narrow by a factor of 2. And the -1 here on the outside means it got shifted down 1 unit. And the last one, there are 3 changes. There was the negative here on the outside. There is the +8 on the inside. And then there is a +9 on the outside. So that means it got reflected in the x-axis, so now it's opening down. Okay, inside is either left or right movement, plus is the opposite way, so this is shifted to the left 8 units. And then the +9, the number at the end is always the plus or the up or down movement, and this means it got shifted up 9 units. So now we're going to do one last type of problem. We're going to put it together and actually perform the transformations on an actual graph. Now notice the notation is different. They're telling you that this graph right here is f of x, which is is like our parent graph. But the parent graph is just your typical y equals x squared. But all the transformations still occur from your main graph. So if they're calling this one your main graph f of x, and then they're telling you to perform this transformation, the numbers are going to work exactly the same as what we just did. If it's inside the parenthesis, it's going to move either to the left or right, and if it's outside the parenthesis, it's going to move up or down. If there's a negative on the outside, it's going to be reflection. So it's all the same transformations, just the notation is in function notation. So inside parentheses is either left or right. The negative is the opposite way what you think. So this means it's going to shift to the right 4 units. And the +3 on the outside, this is going to shift up 3 units. Okay, so what would this look like? So if I take my starting point right there, I have to count over 4 units to the right and go 3 units up. That point will land there. Now all I have to do is do this to every single other point. So this point right here is going to go over. This point right here, go over 4. And this point right there, go over 4. Now if you notice, it's going to just do the same pattern on the other side. You can just go with it, or you can count from the other points. And there is the graph transformed in the way they're representing in the function notation. Shifted over 4 units and then up 3. Okay, we'll try this one more time. Okay, so again, they're given to you in function notation. They're telling you that the original graph they're giving you is f of x, so they're saying that this is your base graph, and then they want you to do that to that base graph. Inside is either a left or right. The plus 5 means it's going to go to the left 5 units. And then the minus 2 at the end means it's going to go down 2 units. Okay, so starting here again, going to go over 5 units to the left, and then go down 2 units. So there's the first point. This point is going to be there. This point. And lastly, this point. And then again, I can do the same with all the other points, or just know that they're going to be right across from each other. Okay, and there wasn't problems like this on the last June's Regents exam.